好吧。
Oh.
So we're very happy to have Wang Hongyu to tell us about electric-magnetic duality in the quantum double models.
Thanks for the invitation. And, the topic is EM duality in quantum double models with scattered boundaries. And this work is based on the paper, which is collaborated with Lin, Cheng, Hu Yuting, and Professor Wang Hongyu. So here is the outline. First, we talk about the motivation, and then we introduce the models with boundaries. The third and the fourth part is a little technical. So we show how to Fourier transform the models and how can we use the Fourier transform models to uncover the EM dualities of boundary series. Something surprising is that we can using these models to understand the anyon condensation and splitting. And finally, we show the relation between the quantum double model with boundaries and the Levin-Wen models with boundaries. So first, let's start with the motivation. We know that topological orders can be well studied by using exactly solvable models, and one major family of it is the quantum double model, which is lattice gauge theory depends on some lattice gamma with the Hamiltonian Hg Qd. And given input data finite group G, this Hamiltonian converts this input data to output data, which is a topological physics, with anyons carry the representations of quantum double dg. This Hamiltonian has two operators, which is AV act on the vertex, and BP operators act on a placket. Both of them gives out the constraints. If the constraint of the AV operators is violated, we see there is charge excitations at the vertex V, and it's labeled by the irreducible representation of finite group G. And if the constraint of BP operator is violated, then we see there is a flux excitations, and it's being labeled by a conjugate class of finite group G. And we can also consider a composition of them, which is called dyons, and it's labeled by the conjugate class C and irreducible representation of the centralizer of the conjugate class C. So since we have the electric and magnetic degrees of freedom, so intuitively, we may think that this quantum double model may have a EM duality. And more precisely, EM duality means if there is a quantum double model defined on lattice gamma, we see there is a corresponding dual model defined on the dual lattice gamma star, such that the charge or flux on the gamma becomes the flux or charge on the dual model gamma star. And this is true in these two papers by Oliver. So they study the EM duality of quantum double model defined on a closed surface, and they found that they found a map from this quantum double model to Levin-Wen model via the Fourier transform. However, they did not consider the topological orders with boundaries, and we know actually topological orders with boundaries are more practical because in real world materials always have boundaries, and if you want to do experiments, boundary modes easier to measure. And something is more important is that if you want to complete dynamical theory of topological orders, you need to specify the boundary conditions. So that's the reason why we want to examine if the topological orders with boundaries still possess the EM duality, and can we find a map from the quantum double model with boundaries to the Levin-Wen models with boundaries. So that's a motivation. And in order to do that, let's first introduce the quantum model our model extended to be defined on a lattice-based boundary. And for simplicity, we define a model on a trivalent lattice with a single boundary. So the gray part is the bulk, and the right-hand side is the vacuum. Each edge of the lattice is oriented, and we assign a group element from a finite group G to each edge. And this finite group G is one of our input data. The Hilbert space is spanned by all the configuration of these group elements. If I reverse the orientation of the edge and replace the group element by its inverse, then we identify these two states. Another input data is subgroup K of this group G, which characterizes the boundary conditions. And the Hamiltonian has two terms. The first term is the HGQD is the bulk Hamiltonian we have introduced in the last slide. And this HKQD is the boundary Hamiltonian. It also has two terms, AV bar operators and BP bar operators, but now they only act on the vertices and edges on the boundary. Using these models, you can compute many topological observables. I will give you an example. For example, the G equal to S3. It has subgroups, trivial subgroup, Z3, Z2, and S3 itself. So you have 4 boundary conditions. And consider a cylinder. It has 2 boundaries and whose boundary conditions characterized by a subgroup K1, K2. Then using the model, you can numerically calculate the ground degeneracy of all the boundary conditions. Here I show the results. Okay, now we want to check the EM duality, and we want to do it following the following Oliver's paper as they done in the book. We Fourier transform the quantum model with boundary. And for that, any questions about the models? If there are no questions, let's consider the Fourier transform. So to Fourier transform the models, let's first Fourier transform the Hilbert space. Since our Hilbert space is the tensor product of the local Hilbert space of an edge, so we can independently Fourier transform the state of an edge first. And the local Hilbert space on edge is spanned by the states labeled by group elements, and we call it local group basis. And using the Fourier transform, so you just use the group matrix representation of irreducible representation mu. So this D mu, M mu, N mu is just a matrix of irreducible representations. You use it as a coefficient and sum over G. You have the states after the Fourier transform, and the Fourier transform basis is labeled by irreducible representation mu and the matrix indices M mu and N mu. And we call such a state local rep basis. It's easy to check that this basis is also normal by using the great orthogonality theorem or Peter-Weyl theorem. For example, for G equal to S3, we have irreducible representations 0, 1, and 2. And we have group basis, 6 group basis, because it has 6 group elements. And after Fourier transform, we have the same number of rep bases, which is given by 0, 1, 1, 1, 1, 1. Here 0, 1, 0, 1, 2 label the irreducible representations, and this 1, 2 in the second and the third positions represent the matrix indices. For example, this representation 2, it has it's divisional 2 representation, so we have 1, 2 to label the basis states. In general, you have the same number of group bases and red bases because of this this famous formula from the group theory. Okay, now let's consider a more complicated basis here. So it has 10 edges and 5 vertices. So you Fourier transform independently each edges to the run-height side. And at run-height side, you see that each edge is labeled by mu and mn. And vertices at run-height side is open because we transform the group elements on the edges that meet at a vertex independently to the linear combination of irreducible representations. For example, we consider V1 here, and we have G1, G2, G4, and we Fourier transform it to the mu1, mu2, and mu4. But these 3 representations are independent to each other. So there's no reason to fuse them. And if you let them to meet at a vertex V1, then I have to move the matrix indices N1, N4, and M2. Then I have some bases with a lower dimension than the left-hand side. But this basis is weird because I cannot attach it to the trivalent lattice, because now we do not know what does the vertex mean and how to fix it. To fix it, we shall rewrite the basis. And the strategy is, for example, for the V1 here, we can first fuse mu1 and mu4 to some degrees of freedom of gamma. And this fusion process must follow the fusion rules. And it will give out 3G symbols. And then I fuse this gamma with mu2 and result in a linear combination of degrees of freedom of S1. And each of them is aligned with a free ending labeled by matrix indices MS1. And you can check that this process preserves the dimension. And it's quite local. For local, I mean, if I rewrite the
there are no black dots because you have black dots on your screen.
Yes.
There are no black dots here, right? Where are the black dots?
The black dot is only on the boundary pixel. Okay, here.
Okay, sorry.
Yeah, here I only consider the boundary theory, so I just leave the bulk unchanged.
Okay.
And in general, you can also rewrite the bulk vertices, and you have some tails in the bulk, but I will not do that here because I only focus on boundary theory. Because bulk theory has been studied by others. So there's no need to study. You can see that this rewriting is quite local, because if I want to rewrite the V1 here, I only involve degrees of freedom of mu1, mu4, and mu2. I will not involve the like mu9 here. So we see that this S1 and MS1 is the induced degrees of freedom at vertex V1. And we can repeat this procedure for V2, V3, and V4, and for all the vertices on the boundary. And finally, you got some basis on the right-hand side and with some tails on the boundaries. And here the black dots, I mean the 3G symbols. Here I just show the, I just talk about the logic and the physics. I didn't write this rewrite explicitly. And if you work out the details, it's a linear transformation. And so right-hand side should be a sum over gamma S1, MS1, and eta, and all the degrees of freedom you appear on the tails and in the middle of the two black dots. And
sorry, is this gamma S1 also your useful representation of subgroup K?
I will talk about later.
Oh.
This gamma is the irreducible representation of subgroup. Okay, and it's the sum of all the all the gamma S1 and eta, and with some coefficients, 3G symbols. So 3G symbols very like CG coefficients, and you can compute them totally according to the representation theory of the group. So here I list example of the S3. And you can also reading out the without the fusion rule of the irreducible representations. The fusion can happen only if the 3G symbols as non-vanishing value. Okay, now let's Fourier transform the operators. First, we Fourier transform these AV bar operators. These AV bar operators acting on the group basis as a gauge transformation, but average over the subgroup K. And after I Fourier transform it, it's acting on some local basis, as shown as this. And you may think that this Fourier transformed AV operators acting on this local basis, it will modify the degrees of freedom like mu, nu, gamma, lambda. But if you write them down, you find that actually lambda, mu, nu, gamma are already diagonalized with respect to these AV operators. So we just denote this local states as psi as ms. And我重新共享一下。好的。Although the AV operators is diagonalized by it's diagonalized with lambda, mu, gamma, but it's not diagonalized in the basis of representation S. That's not a problem. We can, since it's a projectors, we can diagonalize it with another state called psi s ms tilde, and this psi s ms tilde is just a linear transformation of psi s ms. And after you diagonalize it, the result of this AV operator acting on this local basis is just a dot function. With LA is some sites defined as follow. So here, LG is the site of all irreducible representations of finite group G. And this LA is a collection of all the labels of the value 1 eigenstates of the boundary projectors. And I will give you examples here. So for G to S3, this the site of irreducible representations is 0, 1, 2. And when K is equal to Z2, you see that this boundary projectors is just a two-dimensional matrix, and we can diagonalize it. It's a projector, so it's only have only has 1 and 0 as eigenvalues, and it has 1 plus 1 eigenstates, which we label by psi to 1, and another 0 eigenstates, which we label by psi to 2. And according to the definition of LA, here LA is just 0, 1, and 2, 1. Because 2, 2 is not in this site because it has 0 eigenstate. It's a 0 eigenstate of these projectors. And when K is a trivial subgroup, its boundary projectors is just a identity matrix. So all eigenstates all eigenstates are in the site LA. Any questions here? No, if there are no questions. And we can, and similarly, we can do the Fourier transform to BP operators, BP bar operators. So the BP bar operators acting on the group basis is just project the elements on the boundary into a subgroup K. And we can Fourier transform it. After Fourier transform, you have some coefficient like mu tilde, sorry, it's V tilde and U tilde here. So here, V tilde is the square root of dj tilde, and dj tilde is defined by the dimension of irreducible representations, and this beta j is the Frobenius Shor indicator. But if you consider the cases with no pseudo-real representations, then this beta j is just 1. So you can, for our case, G equal to S3, you can just forget this beta j. And this U tilde here is just the square root of Vj tilde.
So here, so far, we are doing a Fourier transform on the BP operator.
Right.
So far, these are sort of still within the known regime. People wrote down Hamiltonian for the boundary as well. And so right now it is at this step, it's still at the point of translating into a Fourier to the Fourier transform space. Is that correct?
Yes. And no one do that before actually.
Sorry?
No one do that before actually. Yeah, Oliver only Fourier transform the bulk operators.
Okay.
Yes. And here this G is the Wigner's J symbol, and this F factor is defined as following. It's just the sum of 3J symbols with some factors UA, UB, and this omega is a matrix related to the pseudo-real representations, and for complex representations or real representations, it's just identity matrix. So for for G equals to S3, you can also forget it. And I also use the abbreviation of the pair A alpha A. I just write them together, and it's just abbreviation of the pair. Okay, now the subsets appear in the vertex operators, and this F appear in the boundary operators, actually characterize the boundary conditions of the Fourier transform quantum double model. And we denote these two things with the new notion called A, G, K. So let's summarize the Fourier transform. We began with a quantum double model with the boundary conditions characterized by subgroup K in finite group G. And after Fourier transform, we got some group bases with some tails on the boundary. And this group basis can be attached to a new trivalent lattice, differ from the original trivalent lattice by some dangling edge on the boundary, where you put your induced degrees of freedom S and MS on. And this Fourier transformed quantum double model is with the boundary conditions is characterized by this AGK emergent from the Fourier transform of operators. There is still all examples for G equal to S3. We have 4 boundary conditions, and all this subset LA is stable here, and all this F can be computed with 3D symbols. Okay, now let's talk about how to understand EM duality with the Fourier transform models. So EM duality is easy to understood by using the finite abelian models. So let's consider finite abelian group G, and in this case, the site of irreducible reputations is also a group, and it's isomorphic to G itself. So I also denote it as RAP-G. Let's first review the EM duality in the bulk. In the bulk, the AV operators acting on the vertex 1 is just a gauge transformation, and the placket operators acting on the placket P just gives out the finite condition. And after the Fourier transform, we have some operators AV tilde and BP tilde. But now AV tilde acting on the local basis, and it gives out some delta function. So it's much like a BP operator. And the BP operator now acting on the still on the placket, but it's now a gauge, more like a gauge transformation. So this implies that maybe we shall define this AV tilde and VP tilde on the dual lattice. And on the dual, so we can do that because in the abelian group case, the half space of the gamma and the dual lattice is isomorphic to each other. So we can define the BP operators on the dual BP operators on the dual lattice just as the has the same form of the AV tilde operators. And I can also define these AV operators, dual AV operators on the dual lattice as this BP to the operators. And as this identification, if I have a charge at vertex 1, then on the dual lattice, I have a flux. So that's EM duality for the box theory. For EM duality on the boundary, it's very similar to the AV bar operators acting on the local basis is gauge transformation, but average over the subgroup K. And the BP operators acting on an edge on the boundary and in the project degrees of freedom into some subgroup K.
Sorry, for usual electromagnetic duality in bulk, what we call charge, they are representations of the group, and then the flux of the group are labeled by conjugacy class. After you do the Fourier transform, are the flux and electric charge still carries the interpretation as representations and conjugacy class of some other group?
Yes. So this flux, as you can see, this charge at the left-hand side is carry irreducible representation of some, for example, like some group G. For example, like Z2, maybe carry the irreducible representation like -1.
Right, but a Boolean group is easier. What happens to S3?
They happen to S3. For S3 is similar. It is similar because after Fourier transform, if you carry the irreducible representation of
because I meant that if I take the fusion rules of representations, they are not because they have one dimension greater than 1, then the fusion rules looks pretty complicated. But for conjugacy class, I'm not sure if that's why I'm not sure if the fusion of these representations automatically have an interpretation as conjugacy class. Something.
In non-abelian case, I think
probably no, because Yuting's talk was about taking some normal subgroup.
Right.
And then if you take a Fourier transform for the normal subgroup.
But this normal subgroup has to be abelian.
That's right. And then you can tag one group into another. But here, I think in general, it doesn't have an interpretation. It's the representation of.
Right. So for non-abelian group, maybe we not have interpretation. Right. If you want to see the EM duality of a non-abelian group, you show generalize the quantum model to the model with input data by a helpful algebra. Let's see. And for EM duality on the boundary, we have this AV bar operator and also BP bar operators. And if the AV bar operators constraints violated, then we see there's a K charge. And if this BP bar operators constraints violated, then we see there's a G quotient K flux. And we can do the Fourier transform of the operators. And after that, because on the boundary, the AV operators is a gauge transformation average over only a subgroup K. So after Fourier transform is a delta function which restrict this irreducible representation in a subset LA. And these BP operators now becomes something like gauge transformations. And also we can define this AV tilde to on a dual lattice and this BP tilde on a dual lattice. So they become BP star, they become the dual BP operators and the dual AV operators. So now if we have a key charge here on the dual lattice, we have LG quotient LA flux. And if I G quotient K flux, it becomes LA charge on the dual lattice. So that's the EM duality on the boundary. And I think for non-abating case, this picture is also correct, except that now LG quotient LA is not a group anymore. It's become an algebra. Okay, now let's talk about anyon condensation. So surprisingly, we can using this Fourier transform model to study anyon condensation. So we know that in topological phase, some types of anyons can condense and break this phase into a child phase.再共享一下。哎，行了。An equivalent perspective is that we can think there is a domain war between the topological phase and the child phase. If the child phase is vacuum, then we see this gapped domain war is a gapped boundary, and this anyon tabs, which called condensate, can condense on this gapped boundary. An interesting phenomenon is that an anyon cannot directly condense on boundary. They may first split into a number of pieces, and only a part of the pieces will condense on the boundary. So that's a phenomenon called splitting, and this will happen when this may happen when a anyon has dimension greater than 2. But the understanding so far the understanding of splitting is quite abstract, so it's good to understand it in concrete models. So here I just show some examples. This is just a spectrum of the quantum double model of S3, and I use the same notation in Shense and Jiaqi's paper, so you should be very familiar with that. So here the ABC are 3 charges, and D, A, D, F, the flux and other anyons are downs. So as I mentioned, it had the quantum double S3 has 3 boundary conditions. It corresponds to 4 boundary conditions, sorry, and they correspond to 4 anyon condensates. If the subgroup is a trivial subgroup, then it corresponds to the charge condensation, and all the charge condense. If the subgroup is S3, then it corresponds to the flux condensation, and all the flux AFD condense. And other cases like K equal to Z2 and Z3, it corresponds to some it corresponds dion condensation. So some dion condense on the boundary. So what I'm going to understand is that, so you see here, let's C is the charge excitations carry the irreducible representations, dimensional 2 irreducible representations of S3. So why we have two multiplicities here, right? Because in the subgroup Z2 here we only have one copies of C, and in the on the boundary characterized by the charge condensation we have 2C condensed. So now we try to understand with the models. So here is how can we understand it? If I have a charge excitation carry the dimensional 2 irreducible representation in the bulk, and I can move it to the boundary by applying some Hoping operators. And on the boundary, this this irreducible representation is two-dimensional, it must has two states. And in the bulk, these two states are degenerate because they all have the energy as the excitations. And on the boundary, they may be they have the chance to split. For example, when K equals to Z2, the two states labeled by 2,1 and 2,2, and the state 2,1 will condense to the ground state. But 2,2 will not condense to ground state. It's still an excitation state. And when K is the trivial subgroup, all these two states, 2,1 and 2,2, still the eigenstate one eigenstate of the boundary operators. So both of them will condense to the ground states. So this actually explains why we have a 2 here. Okay. Any questions? Okay, if there are no questions, let's talk about the relation between the quantum model and Levin-Wen model's boundaries. So for a Levin-Wen model with boundaries, it's defined on a trivalent lattice with some tiles on the boundary. The half space now is spanned by the configurations of assigning string types, and in the bulk, we assign. For example, for S3, I assign some objects in the fusion category of rep S3, but here we don't need using the category language. You can just think of it as a set of irreducible representations. In bulk, we assign each edges irreducible representations, and an element on another side we assign an element in another side on the tails of the boundary. So this side is a collection of pairs where the first number of the pairs means repetitions, and the second number of the pair represents the basis state of the irreducible representation space. For example, these two is the dimensional 2 representation, so it has two basis states, and we label them by 1 and 2. So you have 2, 1, and 2, 2 here. The boundary conditions is characterized by an object called A. It has two things. First, this is LA prime, which is a subset of LAC, and together with some factors F. This F is different from the F where we emergent from the Fourier transform BP operators. So this F is some factors we obtain by solve some consistency equations. And this F define you boundary Hamiltonians. As long as this F satisfies the consistency equation, this Hamiltonian, the total Hamiltonian, still keep exact-solvable. For example, for the G equal to S3, I can just list all these possible subsets, and solve this F factors. And there are totally 15 possible subsets you can choose, but only 4 of them have solutions. So you only have 4 boundary conditions. The mathematics behind this is called Frobenius algebra, but I'm not going to talk about mathematics today. So you can just think of it as a subset. So you can forget this direct sum here. For example, this A4, you can just think of it as a set with elements 0, 1, 2, 1, 2, 2. And with this factor F solved from some equations. And you may already realize that actually this A1, A2, A3, A4 is just the AG, K we defined before. But I shall emphasize that they are totally different things. Although they have same values, but this A is the input data we choose to define our Levin-Wen model, and those AGK is the emergent things from the Fourier transform of a quantum double model with a specific boundary condition characterized by some subgroup. But this actually indicates that maybe we can just identify this this A and the AG, K. Maybe we have a chance to identify the Levin-Wen model with boundary and quantum double model with boundary. Another evidence is that the ground state geometry of the quantum model on cylinder and coincide with the ground state geometry of the Levin-Wen model on cylinder. So here is the numerical results, and they all correspond to ground state geometry you obtain from other methods like counting the fusion channels of the condensates. For example, if you consider the charge condensation, so the to E here, sorry, I should not write E here, should be the 1. it should be the unit element, but it just means trivial subgroup. And in this case, all the charges condense, and you condense A, B, and 2C. So if you count the fusion channel, you have A, B, and you have 2C, so you have 4, and you plus the AB, so it's 2, so you got 6. And if you count like the 2 and S3, you can see that for the 2 and S3, you have A and D, 2 fusion channels. So you have GSD2 here. So they all equal to each other. But there is a subtlety. If you want to identify the Levin-Wen model with boundary and countable with boundary, you shall enlarge the Levin model's Hilbert space. Another choice is that you truncate the Hilbert space of countable model, but we didn't do that in this talk. To enlarge the Levin-Wen model, Hilbert space of Levin-Wen model, you just using the very similar process as you rewrite the basis on the boundary. And after that, you for each vertices in the bulk, you have a tails. And this tail will support the charge excitations in the bulk. And after that, you will see this Fourier transform Hamiltonian equal to the Levin-Wen Hamiltonian term by term if you identify the A and the emergence A, G, comma, K. So that's the relation, and that's the map we found from a quantum model to the Levin-Wen. Any questions here? Okay, then I finish. So it's just summary. So it's very brief introduction to the topological orders with boundary, and I generalize the EM duality to the quantum double with boundary using the Fourier transform. And surprisingly, we can use the models to understand the anyon condensation in terms of the input data. And also we found a map from the quantum model to the Levin-Wen model. Okay. And yeah, thanks. And any questions?
Did you construct the ribbon operator that describes boundary excitations?
No, we didn't do that.
Do you have any thoughts on doing these things for high dimensions?
For high dimensions, yes, for high dimensions, maybe you can do the same things. So for three-dimensional twisted gauge theory, maybe, but not very easy.
Maybe you can use things like condensation and grains.
But the key point is here. So you can use the input data to understand the multiplicity of the output data. So this is quite interesting because the condensate is also called Frobenius algebra, and this input data is also called Frobenius algebra. So, and what's the relation between these two Frobenius algebra is quite interesting.
Is it that if I take the center of this
center of algebra, yeah, maybe, but I don't know. We can now prove it. Maybe some mathematicians.
both these things maybe in contrast, but that was.
Yeah, I do not understand central algebra. Yeah.
Any other questions?
没事，大家有问题随便问，反正都很熟。
不熟，不熟。Okay. There are not other questions because we can always ask him anytime you want. So this talk will be available online on YouTube. Thank you very much for coming and thanks Wang Hongyu for.
Thank you.